Lauren. Hi, I'm Susan Murray. I want to welcome you all to our February meeting for the Ann Arbor chapter of the ASA. Any announcements?
Hey, I have an announcement.
Well, come on.
All right, where should I stand? Right here or in front of your lab? Okay. I've been asked by the Detroit chapter to make an announcement on, they would like people to please consider joining them and us on Saturday of April 5th for a joint ASA chapter statistical judging awards at the Michigan Science Engineering Fair. All right, it's April 5th. They're trying to have 10 to 15 judges. There's not that much time commitment. They would like to have a couple of meetings, and I will send out announcements via an old email list, but you can contact the Detroit ASA chapter or the Ann Arbor chapter, and you can find more information at a small website, sefmd.org.
You want to copy it in the chat?
I'll do that. Yes, good
Okay.
suggestion. All right, thank you.
All right.
When is the science fair?
It'll be in Lawrence Tech.
Okay, before we get started, I just want to introduce our speaker. Daniela is a PhD student in the Department of Biostatistics at the University of Michigan. Her dissertation combines methodological advancements for the field of biostatistics as well as practical tools needed to more clearly understand correlated time to event outcomes of different types observed in the same patient. Daniela has been a collaborator conducting statistical analysis for the CAPTURE study, a large cluster randomized clinical trial focusing on identifying undiagnosed COPD participants and exacerbation risk in primary care patients. And on a personal note, she is my PhD student, and I'm quite lucky to be working with her. All right, it's up to you.
Sounds good.
Are you in the, yeah, I think you're over there.
Yes, I'm just gonna change here. Thank you, Susan, for the introduction. Hi, everyone. As Susan mentioned, I'm Daniela. I'm gonna talk up today. The title of this presentation is Multiple Imputation of Censored Bivariate Event Times via Inverse Transform and Non-Parametric Sampling. This is it's part of one of the chapters of my dissertation. Under, of course, my advisor is Dr. Susan Murray. All right, wait.
Microphone. Battery pack.
Is it like this? Is this working? Is this on?
It's on.
Okay.
Is that better? Is that coming through?
I mean, I don't have a problem hearing.
I'm worried about turning my speakers on. Check. Hello?
Hello?
It's coming through, but I was trying to mute myself.
Try now.
Hello?
Yes.
Yeah. Okay. So before we start, this is just a brief outline of the presentation that we have today. I'm gonna start talking about bivariate time to event data and when do we see it and what kind of applications do we have. The motivation behind this problem, methods, a simulation study that we conducted, and finally an application. So let us start with bivariate time to event data. So bivariate survival data subject to right censoring arises in various medical research settings. And here I just have a couple of examples. The first one is in an HIV/AIDS clinical trial in which it's of interest to study two different event times. One is just time from initiation of antiretroviral therapy, ART, to virological failure, and the other one is time from initiation of therapy to regimen or treatment change. Another example in a clinical trial settings, which we actually see a lot in my GSI work, is in IPF clinical trials. IPF stands for idiopathic pulmonary fibrosis. This is a disease in which there is some scarring in the lungs. And in this type of clinical trials, we talk with multiple physicians specialized in this disease, and there's like multiple time to events that are of interest to consider in this study. The first one is normally time to death, and the second one could be time, for example, to exacerbations events that are normally measured as time to hospitalizations. You will notice that I have put these two examples here. However, they have a slight difference. Even though they are both clinical trials and they both have time to event data. In the first example, the HIV example, we don't have a terminal event, unlike the second example. And that's just to say that in our methodology, we would like to accommodate for different types of bivariate time to event data settings. Eventually, we would like to accommodate or to understand more of two bivariate time to events, particularly when one is a terminal event that censors the other. However, for the rest of the presentation and what I'm going to talk about today, it's a method that we developed to better understand the first type of clinical trial in which we don't yet have a terminal event. And we'll talk about some future applications where we can see our method changing to accommodate for the second time. Okay, so that being said, methods for analyzing bivariate failure time are still being developed. There's a lot of nonparametric estimators of the bivariate survival function available in the literature. However, unlike in the univariate case with the Kaplan-Meier estimator, for example, there is no nonparametric function or nonparametric estimator that has been just yet available, or everyone kind of like consensus that this is a good estimator to use for this case. So in general, the nonparametric estimation of the bivariate.
I'm working for CMS contractor, so we don't know what the heck's going on.
Barry, can you mute?
You mute him.
Oh, okay.
You mute him.
I should have done that. I think he's.
He's talking to somebody else.
Okay, so.
So please go back to what your other sentence was. I lost it earlier.
I was saying that in general, the non-parametric estimation of the bivariate survival function is still an active area of research.
Right.
Unlike the univariate case, there's no like general consensus about good non-parametric estimator that we could use in the general case. So the problem that we are facing here is, as I mentioned, there are existing non-parametric estimators, such as, for example, Campbell's, Dabrowska, Prentice and Kai, among others. Actually, there's a full list. However, here we just listed the ones that are most commonly used in the literature, and the ones that also have like software available in the literature, which is also kind of a drawback from some of these methods. However, in general, drawbacks for the existing methods are non-monotonicity, non-uniqueness, slow rate of convergence, or lack of asymptotic variance of covariance expressions. If our goal is to be able to estimate this bivariate survival function, if we think of a setting in which we actually observe fully both of those times to events, then the complexities of estimating this bivariate survival function kind of vanish, in the sense that if we were to observe this data, it would be easier to estimate the bivariate survival function because we could use just simple probabilities for which we know their behavior really well, right? We know their asymptotic behavior really well. We know how to calculate these probabilities. The problem, yet that just doesn't accommodate to our case. We do not observe fully these times to events. In the univariate setting, multiple imputation has been proposed to kind of tackle this same problem in the univariate case, where the idea here is that if I don't observe fully these times to event, then I can just, then we can create a methodology, use a multiple imputation method to impute those sensor times that I do not have, combine them with the ones that I do have, and then create a multiple imputation procedure to get the survival probabilities. However, for the bivariate censored case, there are a few parametric multiple imputation approaches, but to the best of our knowledge, there are non-parametric multiple imputation techniques that are available or suited for this setting. That being said, we have a couple of goals for this manuscript. The first one is to develop a non-parametric multiple imputation procedure that is tailored for this kind of data, sensor bivariate time to event data. We want to perform a simulation study, design a simulation study to assess the sample behavior, the sample behavior of our method. we would like to compare to current estimators in the literature, and we have chosen the Dabrowska estimator because it's among the ones that are more used in the literature for this case. It's also a non-parametric it's also a non-parametric estimator of the bivariate survival function. And lastly, we want to apply to our methodology to a real case. Okay, so before we start, I'm gonna introduce some notation, and I will keep this notation throughout the presentation. I'm gonna use capital T is subscript 1, T2, to be the event times with joint survival function capital S of a small T1 and T2 to represent the survival function between those times to event. Here we don't have any assumption about the correlation between T1 and T2, of course. Additionally, we are using capital C to represent the right censoring variables for each of the T1s and T2s. We are using subscript J to be either 1 and 2 to represent 1 or 2 for each of the times to event or each of the censored random variables. And then we also have subscript I to represent the sample individual where I goes from 1 to n. And lastly, we have our very classical survival observed random variables, x, to represent the minimum between the observed and censored time, and then to represent the observed time, and then with the corresponding indicator function that I'm calling delta here. Okay. So I mentioned before in the introduction that this idea comes from, we saw in the literature that people have used this non-parametric multiple imputation in the univariate case, yet it has not been extended to more than one time to event random variable. So what we're gonna do first is just see how the method works and what's the intuition behind just one random variable. So for the univariate case, the imputation works through the inverse transform method. So let us recall what the inverse transform method says. It just tells us that if we have an uniform distribution, let's call it U, then the inverse transform, which I'm gonna call IT in the slides over here, then the inverse transform of the survival function of my random variable of interest, let's call that variable T star, at that value uniform U, then follows the distribution of T star, which just basically says that I have a method to just draw or to sample from a desired distribution using the survival function, using the inverse transform of the survival function and a uniform distribution, right? So how does this apply to sensor event data? Well, imagine I have a subject I who was censored at time CI, and therefore I want to create an impute for that subject in my sample. Taylor et al. Proposed sampling from the distribution of that random variable T star, given that T star is bigger than the sensor time for that individual CI, by changing the survival function in the inverse transform theorem with a conditional Kaplan-Meier estimate derived from the subjects who are at risk at CI. I have an example of how this method works in the next slide because I know it's a lot of what is going on here. But basically what we want to do is just use this idea of an inverse transform method because we have the survival function to create just an impute for that sample individual that it's censored at time CI. Before we do that, we talk about something that we call the risk set. So let us define first the risk set. The risk set with notation RI in my slides denotes the risk set of individuals used to construct that Kaplan-Meier to create the imputation. And basically means that it's the set of individuals who are at risk at time CI. That's all. Just set of individuals who are at risk at that time CI. As I mentioned before, this multiple imputation idea has been studied a lot in the literature for the univariate case. Taylor et al. Were the first one to propose this inverse transform method, but since then there has been multiple approaches that include this inverse transform to create imputations, particularly when one also have covariates in our sample. And so another extension to this method when we have sample is when we have covariates is to include somehow the covariates into the definition of the risk set. And we will use that idea also later in the developing our method. Okay. So the example. Assume please I have a sample and I have an individual I who was censored at time Ci, and for the sake of the example, let that Ci be equal to 0.4 here. So in this slide, this figure is a Kaplan-Meier curve, which is displayed in black, where that Kaplan-Meier curve was created using the individuals in the risk set. Again, the risk set has all of the individuals who are at risk at time Ci, where that Ci is the censored time for the individual whom I'm trying to get an impute from. So I have that in black. I also have in gray Ci just for a purpose of like displaying where that is. And then we want to use the inverse transform method. So how do we use it? First, we need a uniform distribution. Say for the sake of the example, I draw a uniform distribution and that value is 0.8, which is displayed in the y-axis of this plot. So what we do with the inverse transform method is that we map that uniform distribution value of 0.8 to the smallest time such that the inverse transform is less than that uniform value 0.8. So that's what we are doing with those red lines, just mapping that uniform distribution into the curve, and that gets us our impute value. So in this case, for individual I who was censored at time 0.4, that imputed value is, say, around 1.6, where that 0.6 would be divided in two parts. That's 0.4, the time that we observed that was censored, and then the residual time, which is 1.2, wait, I said 0.1. Assume T started, the one that I imputed, it's 1.6, sorry.
Yeah.
And then it would be like 1.2, the residual event time that I have. So that's how the method works for just one individual. However, I have multiple individuals in my sample.
Is
so
it residual because you have to subtract the censored time?
it should be, yeah, exactly. It's residual because of that.
So people are gonna probably be curious about what happens if your U is 0.25.
Oh, that's a great question.
And I think we should repeat the question for people at home if they didn't hear.
So the question would be, what happens if now I have the draw of my uniform distribution, but then the value is 0.25, for example. If I were to map it right now how it is, I couldn't find a map, right? I couldn't find a mapping. So this method works, or we can get an impute or a valid impute from that individual if we have an observed time, right? If we, like the latest time that we have in our sample is an observed time, so that that curve will fall down. We know that that may not be feasible in practice for all of examples. However, one workaround that works really well and that has been used in the literature is just to transform our times to minimum between what we observe and tau, so that we have, and we can guarantee that that curve will fall to 0, and then I can actually have a draw. Does that make sense?
So transform your random variable T star to the minimum of T star and say 3. And suddenly you're imputing a 3 when you have C equal the U equals 0.5.
0.5. Yeah. Exactly. Okay, so we were saying that this is what we would have to do to impute one observation for individual I. I have multiple, possibly multiple observations that were censored in my sample, so I would have to repeat this process for all of those people who I have, who were censored in my sample. So finally, once we do that, we get what we call ITMI, inverse transform multiple imputation survival estimates. So once I repeat the process and I have an invalid impute for all of the people in my sample, I repeat the process m times because this is multiple imputation in a way that I get m completed data sets, univariate data sets in this case, and then I use Rubin's rules to combine and analyze all of these data sets. For Rubin's rules, our ITMI survival estimates are just the average estimates across those M datasets. And then the variability estimates are also given Rubin's rules apply to this case. And we say survival estimates because since we have a completed data set, actually M completed data sets, although our analysis here is kind of fitted to the estimation of the survival curve, we can get any other type of estimates, right? Not only survival. If we would like to get the survival estimates, then we just use sample proportions in this case. Some properties of these ITMI survival estimates. So Taylor et al. Show the convergence of these survival estimates to the Kaplan measure as the number of imputed data sets goes to infinity. As I mentioned before, this method has been extended to accommodate for different settings, particularly, for example, when covariates are also present in the sample, in the way that we can use them in the definition of the risk set. For example, Su et al. Required that the individuals that are in the risk set not only were at risk at that time CI, that the person was censored, but also that they had a similar covariate-derived risk score to those of individual I. And we are going to use kind of this idea in developing our bivariate method. Okay, so now onto the inverse transform for bivariate sensor data. The key idea here is to then again use this inverse transform algorithm, but to modify the risk set in such a way that we incorporate information from the correlated outcome. Before we introduce our approach, we need a little bit more notation. So I'm going to call capital T, subscript JI, upperscript L, to denote the imputed value for individual I for endpoint J, iteration L. Well, where my iterations go from 0 to L plus M, capital L plus capital M. Capital M stands for the number of imputed data sets that I want in my multiple imputation method. And capital L is the number of iterations that I'm going to do of this algorithm. Our algorithm has 3 different stages. The first stage is the initialization stage, in which we incorporate Taylor's et al. Approach in the risk set with Su's et al. Kind of covariate-derived risk score to initialize our method. Once we have valid initializations, we go on to the second stage, which is the nonparametric Gibbs sampler, in which the idea is to be able to draw imputations from the bivariate survival function of those T1 and T2. And finally, when I have all of my data sets, I can get the final M data sets and then analyze them and combine them using Rubin's rules. So we're going to go through each of these stages. So initialization stage, here we have 2 main tasks. The first one is to impute the first time to event endpoint and then to impute the other one. Those are in that order. So to select which time to event we impute first, we are using the rule that we are going to start to impute the time to event J between 1 and 2 with the smaller number of sensor values. That's how we are going to start, that's how we choose where to start. And so for that first, what I do is first I select which of these T1 and T2s has a smaller number of sensor values, and then I just impute that using univariate inverse transform imputation as we saw from Taylor et al. So what I'm saying here is that I'm going to use the risk set that you see on the screen, which is, this stands for risk set for impute for outcome J for individual I at stage 0. And as you can see, it has only one restriction, which is the restriction that ensures that all individuals in the risk set are at risk for that event time J, comparing at time CI, of course. So we do univariate imputation in that first, say, for the sake of the example, that's T1. So I just do univariate imputation there, and I have T1 imputed 1 time. So now the question is, how do we impute the second one, given that I already impute the first one? That's the second task in the initialization stage. So here we are going to impute the remaining outcome. For sake of just notation, that remaining outcome is going to be called 3 minus j. And the idea here is to also do an inverse transform univariate imputation, but modifying the risk set in a way that I incorporate the information that I already learned in the first step. So if you notice here, the risk set has two restrictions instead of just one. The first one is the classic restriction that we have been talking about. I want all individuals who are at risk at that for that endpoint j. The second, though, is the new restriction that we are including. And in this restriction, what we are doing is that we require participants to have outcome j, so the one that I imputed before. So we require participants to have outcome j values that are close in Euclidean distance of those two individual I, which is the one that I'm imputing in this point. Where this closeness of Euclidean distance is defined with a parameter epsilon, where epsilon is just a number greater than 0. We choose this epsilon such that the risk set has at least 5 participants. Yes, which is kind of the smallest value such that we have at least 5 participants. So notice that if we do initialization stage steps 1 and 2, we have a completed data set. However, that completed data set is not what we really want, because the first step does not include any information about the correlated endpoint. So we want to kind of fix that to be able to actually draw imputations from the joint distribution between T1 and T2. And that's what we are doing with the second stage of this algorithm, which we call the nonparametric sampler stage. So in this stage, what we want to do is to be able to draw imputations from the correct distribution of T1 and T2. How do we do that? So when we borrow this idea that if the conditional distributions, if we have conditional distributions and I want to sample from a multivariate distribution, we can use the Gibbs sampler, right? Particularly when the conditional distributions are known. So we kind of borrow this idea, however, we make it non-parametric. And how do we make it non-parametric to grade the imputes? Just through inverse transform and modifying the risk set such that I have a conditional distribution in the risk set. At each iteration L, and then here I go from 1 to L, capital L plus capital M, I alternate between which endpoint I'm imputing first, and then I'm drawing imputations from the conditional distribution of one time to event given the other, and it remains non-parametric because I'm using the inverse transform method, where I use the risk set to impose a restriction in which the Euclidean distance between those times two events are close. Okay, so how does this risk set kind of looks like? And this is just a generalization for all of the iterations. For outcome time, for each of the outcomes, we have 2 restrictions. The first one, again, just I want everyone who belongs in the risk set has to be at risk at time CI for each of those type 2 events. But then I have a second restriction in which I require participants to have a close Euclidean distance for the counterpart outcome. So for example, for outcome type J, I have a restriction using outcome 3 minus J, and for the outcome 3 minus J, I have a restriction using the counterpart outcome. And what we are doing here, if you notice, is that for each iteration, I'm using the most recent imputed value from the endpoint counterpart. So for example, if you notice the risk set for time J, I have a condition, the second restriction, with iteration L minus 1,
Right.
which is the closest one, the one that I have.
That's why that's different. That's why it's L minus 1.
Yes, that's
The
what.
closest one to the,
No, that's L minus 1. It's because I'm using the inputs from the previous iteration. So I'm using Yeah, I'm using the inputs from the previous iteration, exactly. And you can see that, for example, for outcome J, I'm using the counterpart outcome, which is 3 minus J, which is the subscript in my notation.
How often do you update in that if you have to impute for 10 different individuals? You impute a value for one of them and now it might be in the risk set for the second one and the third one? No, you do them as a.
Yes, great question. Yes, I don't, in each iteration, I do not update. I update after the iteration, exactly. Okay, and then once I do all of the iterations, then we go to the final stage, which is we have n completed data sets, which go from time iteration L, capital L, to iteration capital L plus n. And then I combine them and analyze them using Rubin's rules. Again, this here depends on what you are looking at your data sets. For the sake of this example and the simulation study that I'm going to show, we focused on estimating the bivariate survival function. But because we have completed data sets, you could estimate any other type of bivariate or even univariate parameter. Okay. So simulation study design. So we designed a simulation study to assess the final sample performance of our method. We generated correlated exponential distributions to represent the event times T1 and T2. And then we also generated sensor times that from a mixture distribution of Bernoulli and uniform random variables. We set an administrative censoring at tau, precisely so that when I'm doing the imputation, I can have the mean T and tau. And then we considered various marginal censoring rates, so approximately 40 and 50%, and also different sample sizes of 100 to 50 and 500. We compared our results to the Dabrowska estimator. Particularly for the results that I'm going to show you, we used a correlation of 0.5 when generating those correlated exponential using a Gaussian copula. And we also created, in general, different simulation designs, not only with exponential, like changing distributions, changing also the censoring distributions. However, results are kind of consistent in between the different sampling scenarios. So I'm just going to show you one of those. We calculate the following metrics across 1,000 replications of the simulation design. First one, average bias and standard error of our estimates. Second one, empirical standard deviation of our estimator. Third one, 95% confidence intervals. We created those confidence intervals using a log-log transformation to make sure our estimates are between 0 and 1. For those, we have 95% confidence, 95% coverage probabilities and average length. And then we finally have two efficiency measures. The first one, asymptotic relative efficiency of our ITMI estimator relative to Dabrowska's based on empirically calculated survival estimate variances. And we have a second efficiency measure, which is asymptotic relative efficiency for a particular estimator if no censoring was present relative to the same estimator subject to censoring for that scenario, using, again, empirically calculated survival estimate variances. And I'm going to talk about what they mean and the numbers that we see in a later result. So the first result that I have here is this plot that it shows the average bias in the bivariate and marginal survival estimates at small t1 equal to small t2 equal t. So remember that because we have a plane, we have multiple points that we couldn't have plot. So we just chose to plot t1, small equal to small t2 equal to t, which is this x-axis that you see here. And then in this plot, there are three different panels. The bivariate panel, which shows the average bias in the estimation of the bivariate survival function. The middle one, average bias in the estimation of the marginal survival function for T1, and then the marginal function for T2. And what we have is three different methods that we tried. In blue, we have the Dabrowska survival estimator. And then in red triangles, we have our method, but only using the initialization stage and then generating the 20 data sets. In this case, we use 20 data sets. So kind of to see, the idea here was to see what is that we are doing by generating L iterations of our method and if we can get some improve after that. And then in green rectangles, squares, in green squares, we have the full extent of our method, meaning that we did the initialization stage, then we did the non-parametric Gibbs sampler, and then after that we draw the imputations, and then we got the 20 imputed data sets. So there are a couple of things that we want to highlight in this plot. We'll start with the bivariate case. So what we want to highlight in general is the bias increases as a function of time, which, yes, the bias increases as a function of time for kind of all of the three methods that we see here, particularly bigger for the red triangles, which is our method only with the initialization stage. And then when we compare our method with only the initialization stage to our method, the full extent with the non-parametric sampler, what we can see is that we managed to reduce that bias significantly. However, we see that Dabrowska still has like less bias, particularly at the very end tail of the distribution. We also want to highlight that marginally, all three methods, even just the initialization stage, performs really, really well in terms of bias. There's kind of no difference at all. If you don't see three lines, it's because they are just all one on top of the other. Okay, and now we have this table, and it looks like a lot, but bear with me, we're gonna go through every single thing that we have here. So the first thing to remember here is that I'm showing results for exponentially distributed random variables that were censored using a mixture distribution of Bernoulli and uniform distribution. 50% of marginal censoring, meaning that kind of approximately T1, 50% censoring, T2, 50% censoring as well. And yes, and that's basically it. What we are seeing in this table is that we are comparing the Dabrowska to our method with all of those performance metrics that we saw before. The rows in this table, so as you move down in the table, the difference is that we are looking at a different place in the survival distribution, where we are decreasing the survival value. We start in the kind of 75 percentile, and then we go down 0.5, 0.342, and so on until 0.2, which is the last row. So those are the rows. I'm looking at different places in the survival, bivariate survival plane. We have our method, Dabrowska and ITMI, which is our method, bias, which we already talked about. And then the first column is the standard error. So average standard error. So what we mean by average standard, what we want to highlight in this column is that notice that as you go down in the table, moving that we are decreasing the survival value, we can see that our method has a smaller average standard error compared to Dabrowska's, quite significantly vary at the end of the distribution, particularly. Then the next column to that is a standard deviation, and we want to highlight basically the same. As you move down in the table, we see that our method has a smaller standard deviation compared to Dabrowska's. And that difference becomes even more and more larger as we move to kind of tails of the distribution. Okay, then we have the 95% confidence intervals based on a C log-log transformation, complementary log-log transformation, CP, coverage probability, and AL, average length. So there are a couple of things to highlight here. In general, we see that the coverage probability is kind of, for some of these values, within the expected variability across the 95% nominal level. However, when you move down in the table, we can see that both Dabrowska's and our method kind of differ from that expected variability to a very similar degree, where Dabrowska is kind of overshooting that coverage probability, and we are very under that coverage probability to a very similar degree. With the average length, we kind of see the same behavior as we see with the standard error, which is expected. That's how we create the confidence intervals. So the average length of our confidence intervals is smaller compared to Dabrowska's, particularly when you move down in the table. Then we have the efficiency measures, and here is where we see very, very interesting things. So then again, the first efficiency measure, asymptotic relative efficiency, the first column there, between our method and Dabrowska's. So that's asymptotic relative efficiency of our ITMI estimator relative to Dabrowska based on empirically calculated survival estimate variances. This means that values greater than 1 represent higher variability, right? And so what we see is that in general, those are all numbers greater than 1. But when you move down in the table, you move to the tails of the distribution, those values are beginning to be more and more further from 1. So we are more efficient in that sense compared to Dabrowska's. And then the second efficiency column that we have, the last column in this table, is the asymptotic relative efficiency for any particular estimator, either Dabrowska's or ours, if no censoring was present, relative to the same estimator subject to, in this case, 50% censoring, again, using empirically calculated estimate variances. There are two things that we want to highlight here in this particular column. The first one is that, as expected, both estimators kind of lose efficiency as censoring is introduced, meaning that all of those values are greater than 1. However, the second thing that we want to highlight is that, again, as you move down in the table, you can see that Dabrowska's loses more efficiency when censoring is introduced at the tails of the distribution compared to our method. Yes.
So you're more sensitive or more efficient at the tails of the distribution. And that's where, there's less information in the tails?
Yes.
So that's where it's really helpful to be more efficient. Very good, all right.
Okay, so then again, this is just a simulation result for one particular simulated study design with exponential distribution and 50% censoring and all of these things. However, we did replications of our method changing various things, censoring, sampling, sample size, distribution of the event times and censoring, and we see kind of the same conclusions that we just talked about.
Did you look at something like mean squared error at all, where you're including the bias and the variability?
We did see it, but we don't have it in the table, and it's funny because I proposed not that long ago, and one of the faculty members in the committee kind of said the same thing. Like probably we should use that column in this table.
There are all kinds of examples where you trade variance and bias, and where one matters more than the other. So it's not necessarily the right thing. That's one way.
Okay, and then lastly, we kind of did a study case. So the Caribbean, Central and South American Network for HIV Epidemiology has a repository of HIV data from Central and South America and the Caribbean. This repository is easily found in GitHub or Google in general. So we have data from approximately 7,000 HIV/AIDS patients that are initiating antiretroviral therapy across 5 different regions in Latin America. And from this data set, we have two event times that are of interest. The first one is time from initiation of antiretroviral therapy to regimen change, and the second one, time from initiation of therapy to virological failure. With this data, we want to estimate the bivariate survival function where we know that both random variables were subject to univariate right censoring in this case. Okay, so in this plot, first of all, we are comparing Dabrowska's, which is right panel, your left panel, and then our method. And what we have here is a heat map, a contour plot over superimposed with a heat map, where the contours in those plots are the estimated bivariate survival function, and then the colors of that heat map represent the average length of 95% confidence intervals, where here you can see like the colors in the average length. Although it kind of seems a little bit that those contour plots, the bivariate survival doesn't match exactly Dabrowska's and our method. When you see the data to the estimation of the bivariate survival function through both of those methods, it's similar to a third decimal place. The difference is because I didn't create the conv plots, I used a package to create the conv plots, and I don't know what's going on there. That's something that we know we have to correct from this plot. But I can assure you that to a third decimal place, those bivariate survival probabilities are the same. What is interesting and what we want to highlight from this plot particularly is the different behavior, the very, very different behavior between the confidence interval from both estimation methods. So the color in the map, the reddish colors represent like narrower confidence intervals, where purple colors represent like wider confidence intervals. And just by looking at this plot, you can see that as you move for the tail of the distribution marginally, either T1 or T2 in either direction, you can see that you get way wider confidence intervals using Dabrowska's compared to our method. Where again, estimation of the survival function is same to a third decimal place.
How come the 0.3 curve is absent from the plot on the right?
Yeah,
It just happened to be. Okay,
yes.
never mind, doesn't mean anything.
Yeah,
Next question, that's fine.
haven't found a package that lets me kind of decide what contour plots I have want. Yeah.
You're at the mercy of the graph.
Okay, and then finally, some conclusions about this method. So we introduced an inverse transform multiple imputation that is tailored for bivariate time to event outcomes where none of the outcomes are terminal. Our simulation demonstrates that our method effectively emulates the joint survival function. A particular characteristic that is kind of elusive to a lot of non-parametric methods that are already there in the literature is that our estimates are monotonic, whereas, for example, Dabrowska's is not a monotonic estimator. So that's something just to highlight. Coverage probabilities are similar in quality for both ITMI and Dabrowska's, aligned closely to the expected variability around the 95 nominal level. And then finally, our results suggest that the full efficiency of the Dabrowska estimator in general case is unlikely. This is important because we have also looked very deep into this Dabrowska estimator, and it is known that the estimator is fully efficient when all time to event and all random censoring random variables are independent from each other. However, in the more general case, there's no definite proof. And although this is not a mathematical definite proof, this is our suggestion that that's definitely unlikely. And that's it.
That's it.
How long is the computation time of yours relative to Dabrowska's?
It's very, very similar. I even want to say that even for the 6,000 kind of 7,000 patients here, I didn't make a difference.
But so you did a simulation of 1,000 repetitions of all this and
Yeah.
they were similar, great.
What is it?
I was just gonna say, is it available yet?
Not yet.
That's a good question. Gimme.
Yeah.
I can let you know.
Yeah, well, it's like GitHub, that's what I want to know.
It will be.
One of the examples you gave was with IPF patients who have the competing risk of like death and time to first hospitalization. When you do the imputation and the iteration back and forth, do you ever get like fully observed data sets where like death happens before their first hospitalization? And
Yeah.
how do you deal with that, or do you not consider it here?
So that's a great question. So in this particular method, we do not consider that case. We don't work with terminal events or competing risks, but my next project, stay tuned for that, is replicating this method, but feed it to more realistic also other type of clinical trials, in this case where we can have an terminal event. We have a couple of ideas of how we could handle that, but mostly related to the risk set and what we include on.
Is she saying that certain things happen when you get a terminal event before the hospital stay? Is that what you're saying, that, you know, and that's not something that the analysis knows how to handle? Is that the
Well,
issue?
so.
I don't know what the issue is.
So the issue is, even Dabrowska's method doesn't allow dependent censoring. It has to be independent censoring, so if you have a terminal event, you don't get to see the other event, and it's dependently censored because it happened due to a death. So right now, this method and the other methods that do this don't account for that situation. But she's gonna fix it so that even if you have dependent censoring, you can use this.
Yes, that's the idea.
And hopefully we won't have that happen, but we don't know.
Yeah, we don't know,
That's-
but hopefully that
figure it
doesn't happen.
We have to figure that out, yeah.
Yeah, it's a corner case. The impact on the confidence intervals when they get they seem to stay relatively narrow, or stay small. That's helpful when you're looking at the edges of the distribution or these areas. Right? I mean, people want to know that. That's desirable, right?
Yeah, that is a desirable characteristic in general. This confidence intervals is precisely when Dabrowska's confidence intervals, when you go down in the survival curve, like to details, those intervals tend to be bigger and bigger. And that's, yeah, we don't have enough data probably there.
And does that have an implication on the then conclusion from the treatment then, because it's too fuzzy? You can't make any, I mean, in Dabrowska or?
Well, right now, there's no treatment comparison here, it's just a curve that has.
I'm looking for the implications of the improvement. That's, how does it help, how does having a narrower confidence interval help for downstream?
Well, in general, I would say narrow confidence intervals are preferable.
I
from-
understand that. But in terms of how you're gonna use it, it just is that I know this better right now. I'm thinking about how to make use of that.
Yeah.
And maybe
no.
that's outside of the scope of this conversation.
No, this is definitely a paper that will generate spin-off papers because. You wanna do more than just bivariate survival when you have these two things, right?
Yes.
I
Right,
think so.
and something that I don't even think was appreciated here, because not many people think about this stuff, is the margins. When you use information from one margin to predict the other margin, you really are recovering lost information that happens when you have censoring. So even the marginal distributions have narrower confidence intervals than the Kaplan-Meier for those margins. So there's definitely information being used overall to improve the estimation, not just joint, but marginally. And there are implications down the line for how to use this.
Thanks. That helps. I couldn't articulate my question very well. Thank you.
And I want to think about it for a while. All right, well, clearly I love this work.
I thought even Mark Vanderland's name show up anywhere.
Oh, it's in the paper.
It is in the
Okay.
paper, yeah.
This wasn't today.
Yeah, no, definitely it's in the paper, and He also suggested that, I shouldn't be answering this, right? It should be you.
He is in the paper. He has done a lot of work in the Dabrowska estimator, just understanding the Dabrowska estimator and some of the questions that we have about that estimator. And then he has his own non-parametric estimation of the bivariate survival function. Yeah. So that's also something that we talked about in the paper. One of the downsides that we see is that it's an estimator that is very difficult to calculate. And so far, we haven't found software that calculates it, or like some sort of procedure that would make that calculation easier to be able to compare to his estimator.
There's also something about monotonicity that I don't think you mentioned today. Do you want to tell people about the monotonicity of your estimator versus others?
Yeah, I did mention that
Oops.
Dabrowska's
But that's true
Probably
for,
worth mentioning.
that's true for Mark Van Lin's paper as well. He doesn't have monotonicity for the bivariate survival estimator he has. And this just because it's based on sample proportions, it does. Which is quite nice.
So are you getting some up and down?
yes, in the Dabrowska
No,
you can get some.
Not with this, because
But with
it's-
the Nebraska?
Yes, you can get some up and down.
Yeah, it does, and so does Mark Vanderland's. You can have like negative point mass, you know? So this dodges that problem.
Yeah.
Completely.
By introducing a little bit of bias to get rid of those negative points probably.
You know, somebody in her proposal mentioned that it's probably the tails don't have enough people in the risk set that are close.
Yeah.
So probably all you have to do, what was the sample size for those? I can't remember. Well, probably, they said all you probably have to do is have a bigger sample. And then suddenly you'll have more of your neighbors and the tails and the bias will go away.
Yeah.
Cause they probably are, the only the few people in the tails that are reaching backwards and not just,
It's reaching.
you know,
That's
the
what
further.
we saw in the simulation, solved the problem for the first 2/3 of the risk set.
Yeah, but what was the sample size for the simulations? I forget.
This one 100, but we tried
100.
50.
So if you upped it to 500, that might go away. If we
Yes.
get a review back, we might wanna, you know, just remember that comment that 100 is a pretty small sample size.
Yeah.
And the risk set in the tail might be kind of noisy.
Mhm.
Especially if you have 50% censoring, you only 50 events.
Yeah,
Yeah.
And then you're requiring them to be close to each other.
Yes.
yeah.
So you're-
But Dabrowska does pretty, I mean, in terms of that,
It's
Dabrowska's not biased,
incredible.
even with 100, that's pretty good.
Yeah.
So yeah, there's probably some asymptotics going on here that, you know, hasn't fully played out in the tails. But we really wanted results fast, so, and it seems like N equals 100 was a good idea at this time.
Is that the price you pay for monotonicity, the bias?
A little bit of the tails, probably.
I think we could probably show it going away for N equals 200. I bet we could show it goes away, but
Yeah.
for smaller sample sizes, I think you do have a little bit of a bias. It's like 0.01,
In the
so
tails.
it's not a deal breaker. But it is a bias.
So it's, yeah. The Dabrowski is unbiased, but inadmissible because of the non-monotonicity
Yeah, that non-monotonicity
Well,
is.
it's more variable.
trade-offs.
It's not really using the information from the other endpoint efficiently when it does the estimate. And I can't really explain how it is not doing that.
It's like a good time. I think we haven't really thanked our speakers, so I'd like to